there, meteorology students. It's time to talk about how we get air to be saturated. I mean, as we've seen already this module, it's important for an air parcel to become saturated for things that are interesting in weather to happen. A famous quote in meteorology that's often attributed to Ben Franklin, although I doubt that's true, is "no water, no weather." Okay? Almost everything that you and I think about as being interesting weather involves water, right? We need to be able to change water vapor into liquid water or eventually into ice, if we want to talk about winter weather or something like that. So getting an air parcel that is originally subsaturated and making it saturated so that we can start condensing out liquid water droplets and dropping them as rain or whatever is going to be fundamentally important to what we're doing. Now, just to review, remember, the measure that we use to describe how close an air parcel is to being saturated is relative humidity, which we tend to abbreviate as RH. And, well, we learned last time that there were two ways we could increase the relative humidity of an air parcel. One was we could moisturize, well, we could increase the amount of water vapor that's in the air, or we could lower the temperature of the air. Remember, just to review, that's about the dew point of the air. The dew point is a measure of how much water vapor is in the air. We express it as the dew point temperature, where that is the temperature to which we're going to cool the air for it to become saturated. All right, these are two different techniques that we have to increase the relative humidity of the air. Let's kind of take that apart a little bit and see what we can learn about those things. So I'm going to be building a list over here on the left side of the screen that shows the different ways in which we can be increasing the relative humidity of the air and bringing it to saturation. And even before you took this class, my guess is you could have guessed the first one. You wouldn't have guessed this weird vocabulary word, moisturizing. Always sounds like a strange word to me, but we could moisturize the air to bring it to saturation. We could literally add water vapor, increase the vapor pressure of the air. Relative humidity is just the ratio of vapor pressure to saturation vapor pressure. So if you increase the vapor pressure of the air, you are increasing the relative humidity. You are bringing the air closer to saturation. And the truth of the matter is that does happen in the atmosphere. We talked about ways of adding water vapor to the air in the last lecture. We talked about things like a humidifier in your house in the winter adds water vapor to the air that's being warmed by your furnace. But there are natural ways in which this happens too. For example, certain types of fog happen when the air becomes saturated due to evaporation off the surface. Certain types of fogs that happen over lakes, like what you see in this picture, for example, happen as the air becomes saturated due to evaporation of water off the surface, okay? Let me take a moment to point out that your book gives a list of something like 7 different types of fog, okay? I'm not sure I'm nuts about learning about 7 different types of fog, but some types of fog do happen this way, by saturation, by moisturizing, all right? And another example of a way in which we can talk about bringing air closer to saturation by moisturizing would be what happens below a cloud's base. Okay, when it's raining, for example, and we have a base of a cloud, below the cloud, the relative humidity is less than 100%. If it were 100%, if the air below the cloud were saturated, that'd be part of the cloud too. As the rain droplets fall out of the cloud, they fall into an environment where the relative humidity is less than 100%, and they start to evaporate. But of course, evaporation adds water vapor to the atmosphere. Liquid water droplets in the form of that rain are being converted into water vapor. That's moisturizing. And in fact, we're going to see some pictures about that in one of the coming lectures in this module. But that is making the layer below the cloud closer to saturation. We are achieving saturation by moisturizing. But I'm going to be honest with you, moisturizing isn't a particularly common or effective way for air parcels to become saturated. It might be a good way to increase their relative humidity. Once in a while you can find examples where it increases the relative humidity up to 100% and the air becomes saturated. But to be honest, this is kind of the loser of the 3 methods that we're going to see here. All right. Another important way in which we can get our air parcels to become saturated is the process of saturation by mixing. What do we mean by mixing? We've been talking about this idea of air parcels, okay? Imagine if you could take 2 air parcels and you could combine them. Like, for example, maybe this had one temperature and this had another temperature, and you put them together and get a temperature halfway in between. Or for that matter, you have a vapor pressure in this air parcel and some vapor pressure in this air parcel, and you mix them, and now they have a pressure somewhere halfway in between. Real air mixes. It's what air does, okay? We often in this class will talk about an air parcel, like here's an air parcel with some temperature, we're going to move it over here, we're going to move it over here, but air parcels, remember, are kind of just an idea. The real atmosphere is not exactly made of air parcels, it just acts like it is, okay? In practice, we mix air all the time, and certain types of situations in which we get saturation and the formation of liquid water droplets in the atmosphere and so on do happen due to saturation by mixing. Let me just give you an example of what's happening here in this picture here. This is a type of fog called Arctic sea smoke. And Arctic sea smoke happens as subsaturated air moving in from over the land over to the water mixes with subsaturated air that's near the surface of the water. It's not saturated either, but when you mix the two volumes of air, you do get saturated air. And I'll show you how that happens in just a little bit. But Arctic sea smoke is this sort of kind of wispy fog that happens over, especially over warm water on a cold day, like when a cold air mass moves over the Arctic Ocean or over a cold, almost frozen lake, you get this kind of fog. Okay. Let's explain how this is going to happen. And in order to understand how mixing two volumes of air, which are each not saturated, let's use a better word, which are subsaturated, can get you a volume of air that is saturated or even supersaturated, then we need to understand again something about this graph of the Clausius-Clapeyron equation. Hey, wait a minute. I just said a strange word. Supersaturated. I thought saturated means that an air parcel is holding all the water vapor it can hold. Yep. So what would supersaturated be? It is holding more water vapor than it can hold? Yeah, I'll take that as a definition. That sounds fine. Now, admittedly, it can't stay that way. The air parcel can't stay supersaturated. It will, because it is holding more water vapor than it can hold, it's going to convert some of that water vapor into liquid water. It's going to experience condensation, which takes water vapor out and reduces the vapor pressure back towards saturation. But yes, air parcels, at least for a short period of time, can be supersaturated. All right, let's take a look at this graph here. Remember, we saw this graph of the Clausius-Clapeyron equation before. Again, the Clausius-Clapeyron equation itself involves all kinds of horrible things that you don't want to think about, like differential equations and so on. But a graph of it is a manageable thing, where we had temperature on the x-axis and the saturation vapor pressure on the y-axis. And so we had this graph of the equation. And one way to interpret this graph is that it tells us about different air parcels. For example, any spot on this diagram here describes an air parcel that we could have. Like I labeled a spot there with a red dot. This spot would be corresponding to a particular air parcel you measured. It has some temperature T, which is its location on the x-axis, and it had some measured or calculated vapor pressure, describing the amount of water vapor in the air, and that is on the y-axis. And so we have plotted that point there. We measured some air parcel's temperature and vapor pressure. That's the point that corresponds to it. And in this case here, this air parcel happens to be subsaturated. I can tell it's subsaturated because it is below the curve. Remember, the curve itself shows the height, how much vapor pressure the air parcel would have to have in order to be saturated. So like if we were going to use this curve like we did before, we would go from this temperature all the way up to the curve, and that would tell us the vapor pressure the air parcel would have if it were saturated. But we're below that. We have less water vapor than that. Vapor pressure divided by saturation vapor pressure will give a number less than 100%. In other words, you can think of how close you are to this curve as being your relative humidity. The closer you get to that curve, the closer you are to being saturated. Remember, relative humidity is a measure of how close you are to being saturated. All right, so we have this air parcel here. For that matter, we could have another one. All right, so maybe we're going to be mixing two air parcels. They're the two red dots on this diagram here. One is pretty cold and doesn't have very much water vapor in it. One is pretty warm and has a lot of water vapor in it, but neither is saturated. They are both subsaturated air parcels. Well, when we mix these two volumes of air, we'll get a temperature somewhere in between. And when we mix these two parcels of air, we're going to get a vapor pressure somewhere in between the two of them. And so let's do that. Well, we kind of connect the dots and pick a place somewhere in between the two red dots there, and we'll label it with a green dot. The green dot is, halfway between in terms of the temperature, and halfway in between in terms of the vapor pressure. And look where that green dot is. It's above the curve. Its vapor pressure that it has is greater than the saturation vapor pressure for that temperature. This air parcel is actually super saturated. It needs to convert some of that water vapor into liquid water because it's got more water vapor in it than it can hold at its temperature. We took two air parcels that are subsaturated and did something to mix them, and when we mixed them, we ended up with air that is saturated, or better yet, actually even supersaturated. We have to condense water vapor into liquid water drops in this air parcel. That is so strange. It just has to do with the fact of the nature of this curve here being bowed downward like this. When you connect the dots, when you mix two air parcels that are subsaturated, you can get air parcels that are saturated as a result. This happens in the real world all the time. Probably the classic example of this is contrails. Contrails are those trails that you see in the sky from aircraft. People often think that that's pollution, like you're seeing the exhaust of the aircraft, like that's smoke or something like that. That's not what those are. That's cloud. What you are seeing is little liquid water droplets. What happened here? How did we get these paths? When the jet engines are running, the exhaust that comes out of them is mostly water vapor. It is water vapor because the combustion of jet fuel produces carbon dioxide and water vapor. So what is coming out of the jet engines is largely water vapor. It is an air parcel that contains a whole lot of water vapor. The vapor pressure is quite high. But it's not saturated because the temperature of the exhaust of the aircraft is incredibly high. The air coming out of the jet is not steam. It's air that just happens to be mostly water vapor. And it quickly mixes with the air around it. What's the air around the jet? Well, it's a heck of a lot colder than the exhaust coming out of the jet, and it's a heck of a lot drier than the exhaust coming out of the jet. Both the exhaust coming out of the jet and the air around the jet are subsaturated, but when they mix, they get air that is supersaturated, and water vapor, which comes from the exhaust of the jet, has to be converted into liquid water droplets, which is the trail of cloud that you're seeing. You can tell that this is what's going on if you actually watch the jet cross the sky. If you watch the jet coming across the sky, what you'll always notice is that the contrail itself is a little ways behind the aircraft. The first few hundred meters or so after the jet passes, there is no contrail yet. If this was smoke coming out of the jet engine, it'd be right there, 1 inch behind the jet. But that isn't what you see. The contrail is actually a couple hundred meters behind it. It takes a few seconds for there to have been enough mixing between the dry, cold air around the aircraft and the hot, moist air coming out of the jet engine before there's enough mixing that you now have created air parcels that are supersaturated and need to convert some of their water vapor into liquid water droplets. Contrails are a great example of forming condensation and saturation by mixing. Another classic example is how you see your breath in the winter. When you see your breath in the winter, what you're actually seeing is a cloud. That, coming out of that woman's mouth right now, is a cloud. She isn't smoking or something like that, okay? What's going on? There's air in her lungs. The air in her lungs is relatively warm because it's getting heat from her body probably mostly by conduction. The air inside her lungs is relatively moist because the linings of your lungs are wet and water vapor evaporates off of them into your lungs. So inside of her lungs there is a relatively warm, relatively moist air parcel. But it is not saturated. If you could somehow, measure the humidity inside your lungs, you'd find out it is less than 100% relative humidity. You don't have a cloud inside of your lung. On a cold winter day, the air around you is cold and it is relatively dry. There's water vapor in there too. When it is also subsaturated. The air inside your lungs is subsaturated. The air in the environment around you is subsaturated. When you breathe the air out, air from inside your lungs starts to mix with the air in the environment around you. And if the relative humidity is in the right range and so on, the resulting air parcel is supersaturated. You started off with air in your lungs that was subsaturated, mixing with air in the environment around you that is subsaturated, and you get supersaturated air that quickly has to start converting some of that water vapor into liquid water droplets. It has to start making a cloud. You can tell this by looking closely in the winter as to how somebody breathes. As they breathe out, there is a little gap between their mouth and where you start seeing the cloud. It takes a little bit of time before there's enough mixing of the warm air coming out of your lungs with the cold air around you to start forming the cloud. If this was smoke coming out of her, like she had just drawn on a cigarette and now she's breathing the smoke out, the smoke, you can even see the smoke inside her mouth, right? There's no mixing involved. It's the smoke is just coming out of her mouth. Saturation by mixing is happening and you can see this little gap. It takes a fraction of a second before there's enough mixing for you to be able to see your breath. Now, the truth of the matter is, saturation by mixing is not a hugely important way in which we're going to get saturated air parcels either. Okay? It has certain interesting examples, but this is not going to be how rain, clouds, and snowstorms, and hurricanes and stuff happen. So we're going to need to know how that is. But before we get that far, let's talk about some questions here. Question 1. The air in the room around you right now is subsaturated, saturated, or supersaturated? Look around the room. Unless you are doing this lecture in a sauna or something like that, or at the top of the mountain in a fog and rainstorm, I think we know what the answer is. But let's make sure. Let's take a choice from those 3 options and get some feedback before you move on to question 2.